Okay, so you should see my screen and it has the definition there of linear speed. And so linear speed says, suppose that an object moves on a circle of a radius r at a constant speed. If s is the distance traveled in time t on the circle, then the linear speed v of the object is defined by v is equal to s, which is our arc length, all over t, which is time. So v is the distance. And we use that letter right now for our formula for distance on the arc length. So what's that saying is if you had some point here and we want to know how fast is that point moving over here. And we can figure out how fast that is moving by looking at distance divided by time. So just recall, remember we were looking at before our algebra classes, finding distance. We know distance is equal to rate times time. So S is denoted as our distance for the arc length. So all this is saying is S is equal to rate times time. And if we want to find that speed, all we would be doing is dividing by t. And so r, which is our rate, and in this case is v for our formula, the speed times time. So our speed, again, we could get that by dividing both sides by our time. It's basically our distance formula. It's just different variables that we're using in this piece. And it has to do with going around on the circle. Okay, so that is what linear speed is. That how fast is that point moving on a circle? If we were going and looking at angular speed, let me just talk about it and then we'll pull up the definition. That's how fast is that angle moving. And so the definition of an angular speed, and I couldn't get to my thing to do it, but we use the Greek letter omega. So the definition of an angular speed, omega, of an object is the angle theta, where theta is in radians, is swept out, divided by the elapsed time t. So that is omega is equal to the angle swept out divided by t. So that's how far is that measure of the angle? How fast is that going? So we have the distance, that angle, that measure of the angle over time. So we have these two important formulas. And let's look at that linear speed again. And we can actually rewrite this a little bit. Recall that we were talking about arc length, our arc length S, that was equal to r times theta, the radius of the circle times theta, the in radians. So if we go back into our formula right here, v is equal to s divided by t, and we replace that s with r times theta, we can rewrite this. So v is also equal to r times theta all over t. Well, this is strictly multiplication in here. And so we could actually rewrite this a little differently. We can say, well, this is the same thing as v all times r times theta divided by t. Give us the same thing as we have in the line above. But right here, we had just said that angular speed was theta divided by t. So our linear speed could be found if we know what our angular speed is by looking at our radius times the angular speed. So if you don't want to remember that, we could just remember that our linear speed is s divided by t and go about that direction. Okay, so let's look at what we just talked about, and let's look at some applications that involve both linear and or angular speed. So I'm going to pause the recording while I pull up a question. Okay, so our question in front of us says, a neighborhood carnival has a Ferris wheel with a radius of 30 feet. You measure the time it takes for one revolution to be 70 seconds. So it takes a car on the Ferris wheel to go around to get back to the same spot. It takes 70 seconds. So what is the linear speed in feet per second of the Ferris wheel? And what is the angular speed in radians per second? Okay, so we need to look at the linear speed. Well, that is s. Well, we know that it's one full rotation. So, or one revolution. One revolution is a full circle. And so we know that our full circle theta is going to equal 2 pi. So it needs to be in radians. We know what the radius is. It's 30 feet. And so we can look at what s is, which we know is r times theta. So that's 30 feet all times 2 pi. That would be our arc length, all over the time it takes, which is 70 seconds. So we can reduce it a little bit by dividing both the numerator and denominator by 10. And this would give us 6 pi. Feet over 7 seconds. So to me, that doesn't make too much sense. So let's get rid of the pi and put that in decimal form. So we have 6 times pi, dividing that answer by 7. And so this is approximately 2.7 feet per second. Okay, so if you were on the car of the Ferris wheel, that's how fast you would be traveling to get around to the same, how fast you'd be traveling, 2.7 feet per second. So we want to know how fast is that rotating, that angle rotating. And so we're looking at omega, the angular speed. This is equal to theta, which we know one revolution is 2 pi over the time, which is 70 seconds. Well, 2 goes into 75 evenly, 35 times. And so the angular speed is pi over pi radians for 35 seconds. So again, that doesn't make too much sense. And so looking at what is pi divided by 35. And so this would be angular speed is 0.00, rounding to the nearest 100, 9 radians per second. And if we wanted to, we could, if we wanted to figure out that angle, I was going to say, let's figure out what is that degree per second. So if we wanted to find the degree per second, We want our radian measures to cancel out, so we would multiply this by 180 divided by pi. And so if I did that, I'm not going to round right now until the very end. So that's approximately 5.14 degrees per second. So the next example says the radius of each wheel of a car is 15 inches. If the wheels are turning at a rate of 3 revolutions per second, how fast is the car moving? Express your answer in inches per second and miles per hour. Okay, so we are given how fast that angle is moving. That angle of the rotation in the wheel, that is 3 revolutions per second. So we want to take that 3 revolutions and we want to convert that into a radian. Well, 1 revolution is 2 pi. And so if they're making 3 revolutions, we know that theta is equal to 2 pi times 3, which is equal to 6 pi. Okay, so we want to know how fast this is moving. So if you're thinking about this, 3 revolutions per second. So we know what omega is. We know that the angular speed is 6 pi radians per second. So recall that we can find our linear speed by looking at, from up here, there was 2 different formulas, r times omega, which we know what omega is, so let's just use that one. So this is our radius of the wheel times our angular speed. And so we have here that our radius is 15 inches. So we know that our angular speed, our linear speed, is that 15 inches all times that 6 pi radians over 1 second. So I guess we could multiply 6 times 15. So that's going to give us 90. So we have 90 pi inches per second. So let's look at what 90 times pi is. And so this is approximately 282.74 inches per second. Okay, so that's how fast the car is inches per second, but they wanted us then to go through and figure out what was in miles per hour. So this is where we want to start converting And we had done this on the first day of class by using conversions, multiplying by fancy ones to get what we want. So let's just keep ours right now in terms of pi and not round until the very end. So right now we have 90 pi. We have inches all over 1 second. So maybe let's deal, we want it in terms of hours. And so we want to convert seconds into hours. And so we know that there's 60 seconds, start from seconds to minutes, in 1 minute. That would get rid of our minutes, but we want hours. So that's the same thing as 60 minutes. We want to get rid of the minutes, convert to hours, over 1 hour. So that would change our units from seconds to hours, but we also want to convert our inches to miles. Well, let's first go from inches to feet. We know that there is 1 foot. I know I need to get rid of inches, so inches has to be in the denominator here. 1 foot is equal to 12 inches. I need to get rid of feet and put it into miles. And we have 5,280 feet is equal to 1 mile. So now we can start simplifying our units. And so seconds cancel, our minutes cancel, our inches cancel. Our feet cancel. So we're left with our miles, which we wanted, and we're left with our hours, which we wanted. I would probably start reducing before I multiplied through. But to save time, let's just multiply it through. So we have 90 times 60 times 60. And then I'm going to multiply that times pi. And then we're going to divide that answer. And so right now that's approximately 1017876.02 miles, all over 12 times 5,280 is all that we have left in the denominator besides those ones, all over 63,360 hours. So let's take our numerator, which was 1,017,876 and 200 divided by 63,360. So we would get that this is approximately 16.1 miles per hour. So pull in one of the problems from the homework. It says an object is traveling around a circle with a radius of 4 meters. If in 10 seconds, a central angle of 1/2 radians is swept out, what is the linear and angular speed of the object? Okay, so we want the linear and the angular speed. Technically, if we find the angular speed first, and then we can use that to find the linear speed. So we had said before, we used omega for the angular speed. And so this was equal to the angle, which had to be in radians, divided by time. And the linear speed was equal to the radius times the angular speed, or the linear speed was equal to, another way to write that was your arc length all over time. Okay, so reading through the question again, an object is traveling around a circle with a radius of 4 meters. So we know what our radius is. It's 4 meters. If in 10 seconds, time is 10 seconds, the central angle of 1/2 radians is swept out. So let's look at omega, the angular speed. We have radians, which we want. It's 1/2 radian. Let's put that in there. All over our time, which we're given in this case was 10 seconds. So I can think of this, again, we're dividing by a fraction, or where it's a complex fraction. And so we can think of it, if you want to, as 1/2 divided by 10. Rewriting it as a multiplication problem, this is 1/2 times 1/10. So this would equal 1/20 radians per second. And so the velocity, not velocity, I wanted to say velocity because of that V, but the linear speed, this is equal to r times theta. Well, r in our case is 4 meters, all times theta, omega I meant, which is 1/20. And this is in terms of meters. So if we multiply, oops, I already put that 1/20. Okay, so we got that 4 meters times that 1/20. So this is going to give us back 1/5 meters per second. So 0.2 meters per second. So let's go back and just pull it up and put that into my lab and mastering. I'll pause the video. Okay, so looking and putting it into my lab and mastering, as you can see up here, we got the question correct, and that's similar to your problem 26 on your homework. So we're going to stop there, but I do have student hours that you can come and see me if you need help on homework.